High Availability Disaster Recovery, or HADR, is a database replication method that provides a high availability solution for both partial and complete site failures. With HADR, data from a primary database is replicated to the standby database, which is essentially a clone of the primary. Replication is carried out through log shipping via a TCP/IP connection. We can see in the animation that the clients are sending transactions to the primary. In turn, the primary is sending logs in real time to the standby to keep it in sync. We can also see that the primary and standby keep tabs on each other, or ensure that the other member of the HADR pair is still healthy by exchanging heartbeats. With HADR, if the primary fails, the standby takes over as the new primary. Let's look at an example. We can see that the processing stops when the primary fails. The clients can no longer connect to it, and the standby no longer receives logs. Luckily, the standby is ready to take over as the new primary, and we can use something such as automatic client reroute to redirect the clients to the standby. All of this is transparent, by the way. After we bring back the old primary online, we can reintegrate it into our HADR setup as a standby database. We probably don't want to keep things this way because in a typical HADR setup, the primary would be the more powerful machine, so having the standby act as the primary is a temporary situation. What we do next is initiate a role switch, which brings us back to our original setup. Let's go over what we need to do to set up HADR. Let me be clear that we'll be using a pretty generic scenario here. You can do a fair bit more tweaking after you're more familiar with HADR. First, we set various configuration parameters on the intended primary. A few of these are logging related, but most are specific to HADR. There are various methods for creating the standby database. For our example, we're taking a backup of our intended primary and we'll be restoring it to the intended standby. Some of the configuration parameters we set on the primary must be set to different values on the standby, and that will be the fourth step. Then for the fifth step, we start HADR on the standby and the primary. And in step 6, we confirm that HADR is up and running by using one of the DB2 monitoring interfaces. Finally, we look at an example of a manual takeover operation, and that step is actually not part of the setup, it's optional. Before taking the backup, we'll make a few recommended and required configuration changes for our HADR setup. First, we'll set 3 configuration parameters that enable index logging and rebuild and archive logging. And of course, we must set some HADR-specific configuration parameters. The first 5 identify the primary and standby servers to each other, and the other 2 specify the responsiveness to outages and the synchronization between the primary and the standby. Now, let's create our database and set those parameters. Setting log index build on removes the potential for having to wait for invalid indexes to be rebuilt on the standby if it takes over as the new primary. By setting index rec to restart, we're specifying that after a takeover, all invalid indexes on the primary are to be rebuilt. This process won't prevent clients from connecting to the database. We're setting logargmeth 1 because by default, databases are enabled for circular logging, but we need to make our HADR database roll forward recoverable. We must identify the host name of the local and remote servers. We'll have to swap the order of those when we update that information on the standby, and the address that those servers listen on for HADR communication. The system administrator should allocate the ports so that they're not used by other applications. The main thing to look out for is that you're not using the port number that's reserved for the service name, or that port number +1. We also need to list the name of the remote instance. The standby and primary can have the same value here. But if your HADR databases are under the same instance, make sure that they specify different port numbers for their HADR local service parameters. HADR timeout determines the number of seconds that the HADR process waits before considering that a communication attempt has failed. We're using 120 seconds because that strikes a good balance between false alarms and a too slow response to an outage. The default is actually 120 seconds, but we're including it here to illustrate the point that it's a setting we must think about up front. For HADR sync mode, we're choosing near sync. Now this concept of synchronization is very important, so let's spend a bit of time talking about it before moving on. We can think of sync mode as the level of data protection that we want. The sync mode determines when the transaction is considered complete and is then committed on the primary. Is a transaction complete when the transaction's logs have been written to both the primary and standby's log files? If we want that level of data protection, we choose sync as the sync mode. To illustrate this, we have transactions sent to the primary. The transactions are written to the primary's log file, then the logs are sent to the standby, they're written to the standby's log files, and finally an acknowledgement message is sent. So we can see that in this mode there's virtually no chance of transaction loss, because the standby is very closely synchronized with the primary. Is a transaction complete when the logs have been written to memory on the standby? If we want that level of data protection, we choose near sync as the sync mode. As in the previous illustration, the transaction is sent to the primary. An important distinction between near sync and sync is that with near sync mode, the log file is sent to the standby immediately. There's no waiting for the transaction to be written to the primary's logs first. So in parallel, the log file is sent to the standby and the transaction is written to the primary's logs. Another difference is that an acknowledgement message is sent as soon as the standby receives the log in its memory. In this mode, there's a comparatively less communication overhead. Also, the only real chance of transaction loss is in the case of a double failure before the standby writes the received logs to disk. Is a transaction complete when the primary has sent the logs? If we want that level of data protection, we choose async as the sync mode. So we see that the transaction is sent to the primary, and as with near sync mode, the log is sent to the standby, and the transaction is written to the primary's logs at the same time. The difference in this case is that there's no waiting for an acknowledgement from the standby. In this mode, there's very little communication overhead, but we have a greater chance of transaction loss if the primary fails before the logs have been received and written to memory on the standby. However, using this mode can prevent an impact from transmission delays. Is a transaction complete when the log files have been written on the primary? If we want that level of data protection, we choose super async as the sync mode. With super async, the transaction is considered complete as soon as the log write on the primary is complete. So in this mode, there is zero chance of back pressure on the primary because of slow log replay on the standby or transmission delays. The idea here is that in other sync modes, there might be some sort of congestion caused by the standby having so many log records to replay that it causes the primary to wait for the standby to catch up. This can happen, for example, after log-intensive operations like reorgs. You can probably guess that there's a cost associated with the sync mode that we choose. The more synchronous the mode, the longer the transaction time. So we must balance protection with performance, and also consider network latency and the distance between our servers. If, for example, our primary and standby are in the same rack, we probably want to use sync mode. If they're in different cities, we probably want to use async or super async mode. In the case of our setup, the two servers are both located in Toronto and connected by a high-speed LAN, so we choose a stricter sync mode. And we choose near sync because it provides excellent performance with very low chance of data loss. Now that we have our intended primary configured the way that we want, we'll take a backup of it. Then, on the server that will host the standby, we'll restore the backup image. As I mentioned earlier, we'll need to set a few HADR configuration parameters on the standby. These settings are sort of a mirror image of what we set on the primary. And the backup runs successfully. Note that both servers must be set up so we can retrieve backups from the same location. And after we create the intended standby database, it's in roll forward pending state, which we must keep it in so that it can keep rolling forward through the log files that are sent from the primary. Notice that the host names that we're specifying for the local and remote servers are the opposite of what was set on the primary. Now that our databases are ready to go, we'll start HADR on the standby first. And then we start HADR on the primary. So on the standby here. And we see the command ran successfully. Now on the primary. And the command also ran successfully. How do we know that our HADR setup is up and running? As of version 10.1, the recommended monitoring interfaces are the mongetHADR table function and the db2pd command with the HADR parameter. The db2pd command is the easiest method. We recently made some changes to the way the command output is written to the screen, basically writing one value per line to improve readability. Some of the things we want to look for in the output are the HADR state, which we can use to determine the standby's log shipping status, the connection status, which we can use to tell whether the HADR pair is connected, whether any heartbeats have been missed, whether there is a log gap or a log replay gap. When the standby is first started, it progresses through different HADR states, wherein any local and archive logs are read. After the standby receives all the primary's log data, the HADR pair should enter pure state, which we can see here. Pure state is the steady state that we want our HADR pair to be in. And here's the connection status, which says that we're connected. This field will also let us know if there is any congestion. Recall that I mentioned the primary and standby keep tabs on each other by using heartbeats. To determine whether any heartbeats have been missed, take a look at the last received field to see if it exceeds the heartbeat interval that we have configured. Finally, and this probably bears further discussion, but let's keep it at a basic level for now. We want to determine if there's any gap, or really a large gap, between where the primary is and where the standby's log retrieval position is. Furthermore, we should also look at where the standby is in terms of its received position and its replay position to see if it's falling behind. At some point, the standby might have to take over as the primary. When that takeover is forced, that is, if the primary goes down, for example, we call that a failover. When that takeover is graceful, that is, it happens when the primary and standby are both up and in pure state, we call that a roll switch. That's pretty self-explanatory, because a standby becomes a new primary, and the primary becomes a new standby. We might do this if we're performing some kind of rolling updates and don't want to take an outage. We perform a takeover by issuing the takeover HADR command on the standby. There's also the option of using a cluster manager to initiate the takeover automatically in the event of an outage. For this demonstration, we'll take a look at manual takeover. So we go to the standby, and we can see here in the db2pd output that the role is showing as standby, and we issue the takeover HADR command. After the command completes, if we take a look at the db2pd output, we can see that the old standby is now in the primary role. When the takeover HADR command was issued, the old primary had its role switched to standby, which we can see in the db2pd output. Now, it's unlikely that we'd actually want to keep the old standby running as the primary, so we'll fail back the primary role to the original primary. And if we take a look at the db2pd output, we can see that we're back to our initial setup. We can see by this demonstration that HADR is fast and straightforward to set up. This demonstration took about 15 minutes, but that included a lot of background detail that you should be familiar with before implementing an HADR solution. And a final note, HADR is not a cluster manager. If the primary fails, HADR is not what decides that the database should be failed over to the standby. We can do this manually, just as we saw with the takeover HADR command, Or we can use a cluster manager software such as Tivoli System Automation for multi-platforms, which is included with and is integrated with the DB2 product. We'll be putting together a follow-on video for setting up HADR with Tivoli SAMP, but for now you can read various articles dealing with that topic on DeveloperWorks.